All right, so the topic today is the beginning of chapter 2 in understanding cryptography, which is stream ciphers. But before we do that, we're going to do a little bit of introduction to using the Linux terminal. So here's a terminal. Let me make this a little bit bigger. I'm using when you use a terminal, you have to use sort of a language for interaction that's called the shell language. My language is Bash. If you're using Mac, it might be Zush. Is that a thing? Yeah. So I believe Mac uses Z shell, but the overlap is huge. If you're using Windows 10, then there is a way to use Ubuntu while using Windows 10, and I really strongly suggest that you set that up if you're a Windows 10 user, because you need to know how to use Linux if you're going to be a professional programmer. Often, certain software, there's just no way to use it without having Mac or Linux machine. I'm running into that a lot right now in this genomics project that I'm doing. I need to close this back here. And you guys don't need to read my email. Okay, all right. So now let's just do some basic shell stuff. So here you can see this prompt that tells me where I am. This tilde means my home directory. I should say maybe what that is. So PWD is how you find out where you are in the directory structure. So everything that you do through a terminal, you can also do through the graphical user interface here. So in the background, you can see sort of the Windows presentation of my home directory, but I can do everything that I can do through that interface from the command line, and often you can do things more efficiently through the command line. If I type ls, then I will see all of the files in my home directory, and if you checked, you would see that those are just exactly the same as the files you see over there. These blue ones are directories. That means that I can go into them. For example, let me go to the folder that is relevant to our class. So I'll go to Documents. Now I type DOC, and now I'm going to press the Tab key, and that there's a unique completion of DOC that makes sense. So I type DOC and then Tab, and it just completes the rest. Now I'm going to go to the directory for our class. So I actually have two directories that begin 0 fall 20. One for my calculus class and one for you guys. So I'll type 3 and then Tab again, and there's a unique completion, so I can go in here. I can look at the files that are in this directory by typing ls. So there's a list of the things that are in here. If I want to see more information about these files, there's lots of variations on ls. For example, if I do ll, it will tell me timestamps, the owner, the group owner, the file size, the permissions, and some other things. If I want to see which file was created last, for example, I can do ls-ltrc. That's very useful. So you can see the last directory I was working in is the Perl directory. I actually just implemented DES in Perl for chapter 3. We're going to talk about DES. Yeah, so that's basically it. You change directories using CD. You list the things that are in a directory by typing ls. And you execute programs by naming the program. So, gedit is a popular text editor, for example. So if I do gedit and then hello.txt, then it's back here. Sorry, the text is kind of small, but now it's open to this text editor, and I could edit that text if I wanted to. Often you'll see me use Vim. That's a text editor that you can use from within the terminal itself. There's a little bit of a learning curve involved in using Vim, but I find it fun and rewarding. This isn't made for mouse interaction, but a lot of the things that you normally do with the mouse, you can learn to do them through the command line. I guess Vim is too complicated to explain right now, but if you are in Vim, the way you get out of it is you type the escape key and then colon and then Q and then return, or Q exclamation mark. Okay. So is there anything else anybody would like to see here? So OpenSSL tools are something that we will be using a lot. So to get a random number, so you get 16 bytes of real randomness. You could do that. And so we've talked a little bit about piping. So one thing you might want to do, these are all unprintable characters. So you might want to pipe that output to the hex editor, which is called XXD. And if I do that, then I get the same information, but it's in hexadecimal, so I can understand what it's saying. Another thing that I might do is redirect that output to a key. So this would be a perfectly good 128-bit key. So I'm just making up the file extension there. But what this will do is it will take 16 truly random bits and put them in this file, and then I can do whatever I want with that file, like read it in as a cryptographic key, for example. All right. So is there anything else anybody wants to see? We can come back to this and do it more later. Okay. All right. So in that case, let's go to the slides. And I've been trying to give you guys these slides, but CoCalc has been kind of slow this morning. I will give these slides as soon as I'm able to. All right. So we're doing basically the background for stream ciphers now. So I thought I would begin with a review of hexadecimal. I think everybody gets hexadecimal in 204, but some of you might be kind of, I don't know, you might not have thought about it for a while, and it's important. So let's go over it one more time. So we often have to work with binary data. So as you just saw from the OpenSSL random example, often the binary data is not printable. So if you want to know which characters are printable, those are just this is UTF-8 ASCII, and it tells you which characters correspond to which numbers. So a byte is just a number between 0 and 255. So here you have all of these numbers in decimal, and so those are just that's the decimal value of the corresponding byte. And then this is the character that it represents according to the ASCII code. You can check them all out. Yeah, so that's ASCII. All right, and let's look at the hex digits. So a digit is just is a number that is in a place value number system that is length 1, right? So in decimal, the digits are 0 through 9. In binary, the digits are 0 and 1. And in hex, the digits are 0 to F. So these things all have their decimal and binary equivalents here. So notice that there's an exact correspondence between binary numbers of length at most 4 and the hex digits. So a binary number of length 4 is sometimes called a nibble. It's half a byte. It's kind of cute. So there's an exact correspondence between nibbles and hex. And so there are 16 hex digits because hex is base 16. So F is 15. The reason we use A instead of just using 10 is because we want to use a place value number system. So we want, the traditional algorithm for addition, for example, where you line the numbers up, we want that to work. So you need a single digit to represent the number 10 instead of 2 digits. So this is just a reminder about what number bases mean in general. So using the traditional Hindu-Arabic place value number system, if you have 10182, that means 1. Right? So this is the 10,000th place. This is the 1,000th place. This is the 100th place. This is the 10th place, and this is the single digits place. And so each place, you just take sort of that number and multiply it times the corresponding amount. My 4-year-old in Montessori school is way far from understanding this, but she is trying to understand it with her little beads and stuff. So it's the same thing with hex, except it's base 16 instead. So you have to express this number as a sum of powers of 16. And so this is a typo there. Look, I said 10 to the 0, but luckily that's the same thing as 16 to the 0, which is 1. So you have some hex digit times this corresponding power of 16. And so the digits that you need to do that are just the digits that show up in the hexadecimal representation of the number. So in this case, 10,182 in decimal is equal to 27C6 in hexadecimal. You guys know this this joke? There's this terrible joke. Maybe I can write it here. You guys are going to hate me for wasting class time on this. But it says 31 oct is equal to 25 dec. Do you get this joke? Is it saying Halloween is equal to Christmas? But the joke is that 31 in octal is the same thing as 25 in decimal. Ha 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 ha. Sorry, terrible joke.
Professor?
Yes.
Does the 0x just...
I'm sorry, you cut out there, but I think you're asking about the 0x. The 0x is just to let you know that this number is in hex, because sometimes it's ambiguous. Like if I were to write, let me see if I can write here. So what if I were to tell you do something 100 times. So that could either be a hexadecimal number or a decimal number. So just to make sure it's understood the right way, you write OX in front. So all that does is remove the ambiguity. And this is also how you can declare constants in hexadecimal in your code. So for example, let me clear all this. Whoops. Sorry, sometimes this menu is a little bit slow to pop down. Okay. I'm pressing the wrong button. I'm just an idiot. So if I were to write like a C program, so you could do this in C++ or whatever. So if I did int a equals 12, that would be decimal. But if I do int b equals ox12, that would be hexadecimal. So these would be different values. So I do, %d. So both of these are 12, but b has been declared in hexadecimal, and a has been declared in decimal. So let's see if this will actually run. Yes, okay, so it turns out that 12 in hexadecimal is 18. So this works in virtually any programming language. If you want to use, if you want to declare a number to be hexadecimal, you type OX first. Whoops. Okay, so we'll keep going here. So this is just supposed to be an example of looking at some real binary data. So I downloaded this this picture of blue-footed boobies, these sort of silly-looking things. Blue-footed boobies, it has nothing to do with cryptography, but I understand that when these things have babies, there are 2 babies in a nest, and then they fight to the death. So they look silly, but they have obligatory siblicide, which is not funny. So here's an image, and we can look at the bytes that make up the image using a hex editor. So of course, most of these bytes don't print. When I do these commands in the notebook that are preceded by an exclamation point, these are just shell commands. So you could do the same thing from the command line if you want to. So where there's a period over here, that means that the corresponding byte is not printable. Where it is printable, it prints it. So this ampersand shows up there. And so these are just the bytes of the hexadecimal. Oh, sorry, the bytes of the JPEG. Okay, when you look at ciphertext, it looks like noise. So that's one property that a good cipher has. If you actually encrypt something and you look through the bytes, it should look just like garbage. actually even less structured than this. This is actually kind of structured. You see all these, like, you know, these things in a row. So that is not likely to happen by chance. So you could tell that this is not ciphertext, at least not for a good cipher. So the reason people use hexadecimal is just because it's convenient for the human brain as a way to understand data. So sort of data in the abstract. You could use binary. So here's the same information but in binary. But people just find that sort of chunking it into hex is kind of the sweet spot between, you know, it's kind of like, I don't know, binary takes up a lot of space and it's kind of hard to see any pattern here maybe. It's just a better way to summarize sort of abstract data that could be anything. So just to practice with hexadecimal and binary, so we should get good at converting between the two. That's going to be something that's important for this class. So let's practice doing it a little bit. So what I did is I just took the first line of each of those data dumps to the hex editor. So here's the first line in hex, and then here's the first line in binary. So can you see the correspondence between these? Or maybe a first question that you could ask is, how many bytes are described in the first row? How many bytes do you think this is in hex here? Here's a hint. If you look at a byte, you know, so a byte is just a binary string of length 8. And you break it into the nibbles. Okay, so each nibble is 1 hex digit. We mentioned that before. And because base 2 and base 16, you know, 16 is a power of 2, those number bases sort of play nicely together. So the translation is very easy. You just convert each nibble into the corresponding hex digit and then concatenate them. So this byte is 0x67. So what you get here is that a byte is always 2 hex digits. So a 2-digit hex number is a byte. That makes sense because 16 times 16 is 256, and 2 to the 8th power is also 256. So the correspondence here is FF is this, and D8 is this next byte. Here's FF again, is all ones. E0 is this guy. 0, 10 is, here's 0 and here's 10, which is actually 16. And so on. So in the binary representation, you have 6 bytes on the first line, and in the hex representation, you have 16 bytes on the first line. And inside the hex editor, you'll find that the indexing is base 16. So that's kind of convenient. So let me show you. So if you look at this counter over here, after the first row, this goes up to 10, but it's 10 in hex. So it's telling you that there have been 16 bytes. So you can figure out which byte of the file that you're looking at. Later, we'll learn how to use this same program to change these bytes. Okay. So this is how you translate a byte into a 2-digit hex number. It's very easy. So you can do the same thing backwards. All right. So we've talked a lot about modular arithmetic. Equally important is exclusive OR. This is a very common operation in cryptography. I would say every cipher uses, probably every serious cipher uses both exclusive OR and modular arithmetic. Those are sort of like the ingredients for cryptography in some ways. And so we'll use this like a medieval plus sign here to represent XOR. Here's the XOR of 2 numbers. See, I'm sure you're familiar with this, right? So all you do is you look to see in a certain column whether the 2 numbers are the same or different. So every time they're different, you put a 1. Every time they're the same, you put a 0. That's the XOR operation. One way to think about what's happening here is in each column, you just do arithmetic mod 2. So 0 plus 0 mod 2 is 0. 1 plus 0 mod 2 is 1. 1 plus 1 mod 2 is 0. So it's sort of column-wise modular arithmetic mod 2. Okay. And so here's just, I don't know, here's a question. I should have created a poll here. Why don't you guys take a minute to figure this out? And you can try writing, if you don't know how to do it on paper, it's kind of a lot maybe on paper, to write a quick program in C++ and see if you can figure out what this is. I'm going to give you a second to work on it. Anybody know what's the first digit? I forgot. Let me see. Oops. Okay. Whoops. Sorry, getting way ahead there. I did this in Python, but it would basically work exactly the same thing in C or C++. The only thing that would be different is the print statements. So I take these two numbers. Notice I'm using OX here because I want to indicate that I mean those to be hex numbers. And I'm using this caret as XOR. So remember that in most programming languages, that's not exponentiation. In most programming languages, that is XOR, and it performs exactly the operation that we want here. So here it is kind of printed out nicely. So these are the two numbers in binary. So these are 2 bytes, right? And then you XOR straight down. And then the answer in decimal turns out to be 7489, but the answer in hex turns out to be 1D41. All right. So you should practice that, because in implementing any kind of cryptography, you have to do these XORs and sort of understand what's happening. This will help you a lot with your homework on DES, if not your homework with the linear feedback shift register, which is coming up. So XOR has some really nice properties. So for any numbers, you can think of these as bit strings or decimal numbers or whatever. All of the following things are true. I'm going to call this plus just because it is easier to say plus, but it's XOR, of course, every time. So XOR is commutative. So A plus B is the same thing as B plus A. Anything plus itself is 0. So that makes sense, because XOR is supposed to detect, maybe I should just give an example here as we go along, turn on my annotator. Let's take some number like 1101 and XOR it with itself. So how do we do that? In every column, we write 0 if they're the same. Well, of course, they're the same in every column because it's the same number. So this is 0. So any number XOR itself is 0. You can actually see this first property also, because it doesn't matter what order this comes in. And anything XOR 0 is itself. Let's check that out. So what if I take 1101 and I XOR that with zeros? So the only time it's different from 0 is when it's 1. So what that does is it just copies the number over again. So any number XOR 0 is itself. So this third one is not so obvious. This is kind of a theorem that follows from the first two. So if A is equal to B plus C, then B is equal to A plus C. Let's see if we can sort of work that out algebraically. So A is equal to B plus C, right? And I want to solve for B here. So what I can do is I can XOR in C on the right of both sides. Okay. And then I'm going to use another property which I didn't mention, which is associativity. So associativity means that it doesn't matter which one of these operations I do first. So I didn't say it, but also XOR is associative. So what that means is this C plus C here is 0 because of this rule number 1. And so then you get B plus 0 over here. But what is B plus 0? Well, if you look at rule 2 here, that's just B. And so what you get is that A plus C is equal to B. Right. So canceling things out using XOR like that is very important. So there we sort of derived the conclusion using these algebraic properties. Right. So I'm going to clear. You know, I've encouraged everybody to learn how to do screenshots. Of course, you can watch the video later, but it's also sort of useful to be able to just, you know, like note-taking kind of, but digital version. Sorry. Man, I tend to get scams when I'm teaching this class for some reason. Okay, so we're gonna go from just this stuff about XOR to a really powerful cipher. You could argue that this is the first secure cipher ever discovered in the early 20th century. And if you read the Wikipedia article, you'll find out that it was not really discovered by Vernum, but Vernum came up with some kind of commercial application. I think he was actually encrypting financial information about the stock market using like you know, remember ticker tapes, those things that tell you like when you live in ages past what the current value of stocks are. So we let a message be a number. And so you can think of it as in binary, so it could be a bit string or whatever. So this is not actually any kind of restriction because everything is a number, remember? Now you take a key of the same length. So this is important, that the number of bits that you need to represent the plain text is the same as the number of bits that you need to represent the key, okay? And so to get the ciphertext, you just XOR the plain text and the key. And then by our algebraic facts prove that decryption works, because if you do y plus k, y is x plus k, so x plus k is x plus 0, which is x. So this is decryption. And here's an example. So here's a cute fact. There are certain words that are just hex numbers like beef and dead, haha. So if the plain text is the number beef, and if the key is the number dead, and you do, if you take the XOR, then you get 6042. So now here's the decryption. You just take 6042 and XOR it with dead, and what comes out is beef. Okay, so what are the security properties of the Vernum cipher? The Vernum cipher can be very strong. In fact, if k is selected uniformly at random, then it is sort of the it's the strongest possible cipher. But maybe this idea of uniform randomness is important. Maybe we should say a couple words about that. Hopefully everybody knows what it means. I'm waiting for my pop-up menu to come down. Come down, please. So let's just say we have, you know, in probability theory, this would be some kind of event space or something. Can you just tell me, what does it mean to pick one of these numbers uniformly at random? And what's the difference between just saying at random and saying uniformly at random?
They all have an equal chance of being selected.
Yeah, that's right. Okay, yes. So usually in cryptography, that's the kind of randomness we want, is that the uniform distribution, meaning they all have equal chance of being selected. You could still do this in a random way. Suppose that the probability that one is chosen is like 1/3, and now this is, I'm gonna really run into limitations on my ability to do math here. And the chances that 2 is selected is 2/3, and the chance that 3 is selected is actually 0. Then that's a probability distribution. So if I were to draw from this set using this probability distribution, I would be selecting one of these things at random, but not uniformly at random. Okay, so we'll clear all these. So if the key is selected uniformly at random, that means every key is equally likely. And you compute the ciphertext here. Then if you don't know k, each bit of y is 0 or 1 with probability 1/2. Okay, so what we're saying here is we select each bit of k as 1 or 0 with probability 1/2 in each place. Then no matter what x is, y inherits that same property. So if k has 1 or 0 selected randomly with probability 1/2, then without knowledge of k, y has the same property. So y sort of takes on the randomness of the key, even if the plain text is structured. Okay, so here's a demonstration with a one bit message. I use the NumPy random number generator, and I get a random bit. So if I run this over and over again, I'll get different bits. Come on. Come on, man. Okay, finally switched to 1. Jeez, I got like 6 zeros in a row. What are the chances? Anyway, okay, so this is randomly producing zeros and ones. So if there's here this known bit is supposed to be like x. If I know this known bit, but I don't know the random bit, then I don't know anything about the cipher bit. So because the rand bit, with probability 1/2, this thing is 1, in which case the known bit will flip. And with probability 1/2, this random bit is 0, in which case the known bit will stay the same. So basically this is saying that the bit will flip with probability 1/2, and without knowing what the random bit is, I don't know whether it flipped or not. So I have no information about the cipher bit if I don't know the random bit, even though I do know the known bit. Okay, so there's a famous cryptographer and just a famous mathematician in general named Claude Shannon, he was a World War II cryptographer, and he was sort of the first person to come along and sort of do cryptography correctly. Or I guess that's an exaggeration, but he was sort of like, the American, I don't know, he's the American cryptographic hero of World War II. So he has this theorem that says if X is encrypted with a Vernam cipher using a key that's selected uniformly at random, then Y contains no information about X in the sense of information theory. So there's a mathematical definition of information, which actually Shannon also developed. And so from this you can prove that that a ciphertext-only attack on the Vernam cipher is mathematically impossible. We won't prove it, but it kind of makes sense. Like, if the ciphertext contains no information about the plain text, just take that literally for a second, okay? The ciphertext literally contains no information about the plain text. Then there's no way to recover the plain text from the ciphertext. And so that's what happens because all the information is sort of sucked into the key, and the key is secret. So even alien supercomputers that were harnessing like the energy output of entire star systems or something cannot crack it because you wouldn't even know when you did crack it. Okay. So when this happens, it's called information theoretic security. And it's basically only possible with a Vernam cipher. So Shannon's theorem also says Information theoretic security is achievable if and only if the key is as long as the message in bits. Okay, so this is sort of the starting point for a lot of modern cryptography, because we want to retain the security, but we want to get rid of the requirement that the key has to be long. The fact that the key has to be long sort of ruins everything. If I want to send you a 6 gigabyte file, then we have to have sort of prearranged on sharing a 6 gigabyte secret before we communicate the file, which is really inconvenient and really can't practically be done. So maybe, you know, a lot of modern cryptography is just kind of like simulating the Vernam cipher, but removing the requirement that the key is as long as the message. And when you do that, you lose the information theoretic security, but if you do it in a smart way, often we think that you retain sort of practical security, meaning that that there's no way to discover any information about the plain text without doing like 2 to the 80 computations. So here's an example. I don't mean for this code to be secret. I just don't want it to be distracting. So basically what this does is it takes two strings and then XORs the ASCII. That's what it does. So here's an example. So X is don't look in the bathtub, and K is this is a key, but it's not a random key. So I take the XOR of those two. You know, each ASCII character is just XORed with a corresponding ASCII character. And then what does Y turn out to be? So if you look at each byte in decimal, so this is each byte of Y in decimal, it turns out to be these numbers. And now I'm printing it in another format, which is useful, even though this is just a Python thing. It's useful enough to explain, I think. So look at this. This B here tells you that this is a byte string. So the way it works is sometimes if the character is not printable, then they just tell you the hexadecimal. So this first character in Y is not printable. It's 16. So they just tell you the hexadecimal, which is 10. 7 is not a printable character either. So they just tell you the hexadecimal, which is 7. 73, however, is a printable character. It turns out that it's the alphabetical character I. So instead of giving you the hex, they just print it out. So the rule is, if it's not printable, you get the hex. If it is printable, they just print the character. And if you look through here, you'll notice something that is that's interesting to a cryptographer, which is the places where a printable character pops out are exactly the indexes where one of these things is space. So notice that the I here is in the 3rd slot, and there's a space there. So now if we go 4, 5th, there's another space here in the 5th place. And if you come over to here's the 4th, and now the 5th is just D. It's the printable character D. And so this pattern will continue here. The reason it happens, maybe I can just skip down. Please don't get confused. Just so focus on this cell right here. Okay. So what I'm doing here is I'm playing around with taking the XOR of ASCII space with an ASCII Roman letter. So the XOR of ASCII space is 0x20. So it's what is that, 32, I guess, 32 in decimal. Then what it does is it just flips the capitalization. So that's kind of cool. So if I take lowercase b, the output is uppercase b. If I take uppercase G, the output is lowercase g. So space behaves in this really, you know, simple way with respect to the letters. That's just a quirk of the ASCII code. I don't know if they did that on purpose or what. And so another interesting fact is if you XOR space with any non-Roman letter, then a Roman letter never comes out. So when you look at the ciphertext here, sorry, I need to go back to where we were. If you look at the ciphertext, the places where Roman letters come out, like S and these other places, those are exactly the places where one of the two characters that were in the two streams that got XOR'd was space. So you can identify where the spaces occur with some level of confidence using this trick. So this among other things shows you why K has to be random. Y does contain information about the plain text if the key is not totally random. So if X and K are written in English, like they were in this example, you can identify where space occurs in X with about 50% accuracy. Because you can identify where space occurs in either X or K, and so there's about a 50% chance that the space was in X and about a 50% chance that the space was in K. So I definitely learn information about X, right? I find out with 50% probability where the locations of a space is. Okay, so to get the good properties of the Vernam cipher, it's crucially important that the key is truly random. So now let's talk about how you can get good random numbers. If you go through and look at cryptographic disasters, we should actually, a good student project would be to make sort of a library of cryptographic disasters. And if you did that, what you would find is that a lot of them happen because a number is supposed to be random that's not random. So here, this is something that we've already done. One way to get a cryptographically suitable number is to use the OpenSSL rand function from the command line. Here's how, quote unquote, how to do it. This is made as simple as possible. So on Linux, Unix systems, including Mac, there's a device random number generator. So /dev/urandom. And you can read from this device just like it was a file. So I'm doing it in Python, but it would be exactly the same basically in C or C++. You just read from the file. And so what I do here is I open the random number device, and then I read however many bytes of random data I need. In this case, I read the same as the length of the message. So this just says the key will be random bytes of the same length as the message, and then you XOR them. And here is the random key that got selected using this bytes notation that we've already talked about. Okay, so most libraries come with a random number generator. Like in C and C++, you've probably used rand, right? Those are not the random number generators that you need to use when you're doing cryptography. Those are for simulations and for games and for like, statistical. So those things behave statistically as if they were random, but they don't have the properties that we need for cryptography. The reason is that the outputs are predictable. So even though they have the same statistical properties as random numbers, they don't have the cryptographically secure property of also being unpredictable. We'll come back to that in a second. So let's spell out the downsides of the one-time pad. So you might have noticed that, I don't know, you don't use the one-time pad when you go shopping on Amazon. That's because for every time you and Amazon exchange encrypted information, you would have to already have allocated this huge key that would be as long as all the encrypted information you would ever send. So then there's this problem of how does the key get distributed? This is like this is a recurrent issue in cryptography. It's called the key distribution problem. But if you and I are going to communicate using a secret key, at some point we have to exchange the key, but we can't do that through an encrypted channel because we need the key to have an encrypted channel. So it's like a chicken and egg thing. So at some point, it seems that we have to share a secret. We'll see later in the semester, there are actually brilliant techniques that let us exchange keys without, and actually we can exchange keys through a cryptographic channel, but it's the kind of thing that you would never think of in a million years. It's this genius idea called the Diffie-Hellman key exchange, which you can read ahead about if you want to. But the one-time pad, it has been used in practice in the past. So here are two examples. One of them is Venona project, and the other one is Sig Sally. This is a little bit of a digression, but maybe we can look at this. So with the Venona project, this was, I don't know if you guys have ever seen TV shows about like Cold War spies. Probably because we live in America, you've seen TV shows about Russian spies in America, but maybe in Russia they have TV shows about American spies in Russia. I don't know, but these people did tend to communicate using a one-time pad. So when they came, you know, just to do the American TV version, when the Russian agents came to the U.S., they would have somewhere on them a book that was a literal pad of random numbers. The random numbers were generated by employees of the Russian state who would pick ping pong balls with numbers on them out of like a random basket, like they do the lottery on television. These people, like actually generating the random numbers was tedious, and you know, these people that were generating the random numbers, like pulling out these ping pong balls, understandably maybe got kind of like skeptical about the purpose of you know, like randomly selecting a ping pong ball every time. And so the problem was that the key was not as random as they thought it was. They also made the KGB or GRU or whatever made a mistake in that they used the same pad they repeated the pad, but not on the same continent. So they might have given one code book to people in North America and then another, and then that same code book to people in like maybe the Asian or Australian theater. And the problem is that the one-time pad is called the one-time pad for a reason. And then they were able to declassify decrypt some of these messages. Not much. I mean, there was much more that was never cracked, but anyway, some of the messages were able to be decrypted. There's another famous instance of using a one-time pad called Sig Sally. If you ever read the book Cryptonomicon, which I don't necessarily recommend, I think it's kind of a boring book. But anyway, there's a lot about Sig Sally in that book. So Sig Sally was actually Shannon and Alan Turing were both involved in this project. This was supposed to be a way for Americans to speak freely over a telephone communication, over a telephone channel with leaders in Britain. And of course, they didn't want the Germans to eavesdrop. So what they did is they had this literal record album that was noise. And so they would play the noise on the American end, and then they had the same data in Britain, but it was like the inverse. So if you think about the like sound as a frequency, the frequency was exactly inverted on the British album, so they would cancel each other out when they were played at the same time. You play these two albums at the same time, it's like noise canceling headphones. It sounds like nothing. But if you play just one of them, then it sounds like loud noise. Which is this basic idea is the one-time pad, where the record album is the key. Anyway, so those are two famous examples. All right, but it has problems. But the key must be as long as the message. The key must be random, and you know the lesson of the people picking the ping pong balls tells you that it can sometimes be painful to find real random information. Also, programmers often make the mistake of not using the correct random number generation method. And the key has to be distributed before both parties can communicate. So like in the case of Sig Sally, somebody had to actually take a boat across the Atlantic Ocean with these records in a suitcase handcuffed to their arm or something before they could communicate. So another problem is, why is it called the one-time pad? What happens if you use it twice? So let's see. And you might want to come back to this because you'll probably have to do some kind of exercise at some point in the course where you actually do this. So what happens if the one-time pad is used twice with the same key? So let's just set it up and see what goes wrong. So here we have two plain texts, x1 and x2, and the same key is being used both times to produce y1 and y2, which are ciphertexts. The problem with that is that you can then XOR the ciphertexts. So, everybody knows the ciphertexts because those go out in the open channel. So the eavesdropper knows y1 and y2. So knowing y1 and y2, what can they do? They XOR them, And then if you just look at the algebra here, you'll see that these, the keys cancel out. Okay, so this key and this key, they cancel out, and then you just get x1 XOR x2. So if you use the pad twice, then the enemy knows the XOR of the plain texts, and this is worse than it seems. So one problem is that the enemy may already know all or some of one of the plain texts. So this is the KPA, the known plain text attack that we've talked about several times. So with a 2-time pad, the known plain text attack kills the cipher. You just solve for x2 like this. So you XOR in the thing that you know, and the thing that you don't know pops out. Another problem is that if x1 and x2 are natural, let's just write some things down like hi, how, are, and that's enough. This is going to be painful. Can I undo that? No. So if I write just some English here, and then I write, sorry, I'm kind of messing this up, some more English below, fine, or something. So, we've already talked about how certain letters are more common than others. So what'll happen here is that certain XORs of pairs are more common than others. So there will be like a unique signature of H XORed with F. And if the plain texts are long enough, like, if you do this with a book or something, this would actually be a good exercise. Take 2 books from Project Gutenberg and just XOR them, and then try to recover both books. It turns out that you can do it. It's like a little tedious, but and actually just frankly kind of hard, but it can be done. All right. So, and then even without this sophisticated statistical attack that we were talking about, we've already mentioned that you can infer the locations of where the spaces happen. Let's look at that. And it's for this reason that we've already talked about. So when you XOR with space, it just flips the capitalization. And here's a real example. So let's say that x1 is hi, I am a message. x2 is baloney is so good. And then I take, just to be fair, I take a truly random key. So here's a truly random key. Then you produce the first ciphertext, the second ciphertext, and now you XOR the ciphertexts. So it doesn't matter how good the key was, because it totally cancels out when you do the XOR of y1 and y2. And what you'll notice is that the space trick now works on y1 plus y2, among other problems. So this third place here is a space in x1, so we should be able to detect that down here. So first we have a new line character, and then we have 06 in hex, and then we get the ASCII character L. So because we found that ASCII character, we've detected a space in one of the 2 messages. So that's just, anytime you can infer any information at all about the plain text, it pretty much means that the cipher is broken. All right, so let's talk a little bit more about pseudo-random number generators. We'll kind of try to present this stuff from the top. So random number generators are important in cryptography. One reason is that we can use them to kind of simulate among many applications, we can use them to simulate the one-time pad. So here's an idea for simulating the one-time pad. So we'll take a pseudo-random number generator. So what is that? That's a function that takes a seed as input, and it produces a stream of pseudo-random data. So I can here I just get one random number, but I could get as many random numbers as I wanted to. They were all based on this same seed of 22 here. And if I picked a different, so every time I run this, I'll get the same output because the seed is the same. But if I change this seed, then I'll get completely different numbers. So every time you change the seed, you get completely different numbers. So this kind of gives you an idea for how you might simulate the one-time pad and get rid of the bad properties and keep the good properties. So maybe the secret cannot be the entire key stream, but just the seed. So we'll make the seed be the key. And so this idea basically works, but you can't do it with just any random number generator. Like this numpy random number generator is not secure. And it's not because these numbers don't have good statistical properties, they do. The problem is that if you know 595, 742, and 40, then you can, then maybe you can predict what the fourth one is. So that can't happen because it can't be the case that if you know a little bit of the key stream that you can predict the rest of it. That's a recipe for cryptographic disaster. So so the basic idea of using this trick to simulate the one-time pad key works. It's just that you have to be very careful about what kind of random number generator you use. So what we need is a cryptographically secure random number generator. So the acronym for that is CSPRNG, C-S-P-R-N-G. So cryptographically secure pseudo-random number generators, they still take a seed. The difference is that with a cryptographically secure random number generator, you can't take some of the output and then infer any information about the rest. So the exact formal statement of this is kind of like beyond the scope of the course. It's like too mathematical. But here I try to sort of like, still try to say something about it. So suppose you know n bits from the output of a C-spring. So this is some of the key stream that's been produced using this random number generator. So we know all of these bits except for this one with a hat on it. So we know, like a bunch of them on the left, we know a bunch of them on the right. But these attacks assumes that you don't know too much. You don't know like, you don't know 2 to the 8. If you have 2 to the, if the attacker needs like 2 to the 80th examples to do this, then you can still be secure because you can assume that the attacker will never have this huge number, this huge table of examples. If the attacker has some polynomial amount of data, then you want this property. So without knowing the seed value, there's no way to predict BI, which is the missing one, with accuracy better than random guessing. So even knowing all these other surrounding values, not knowing the seed, the enemy can't predict whether BI is 0 or 1 with probability different than 50%. Okay, so this leads us into linear feedback shift registers. Which is going to be an entire lecture unto itself. We can get started with them now. Does anybody have any questions before we go on to linear feedback shift registers? Maybe we should look through the web work. So the chapter 2 questions are, so they're open and they're due 1 week from today. So let's look through those. Right. Okay, so this stuff should now look kind of familiar, right? Everybody has randomly generated bytes here, but otherwise the problems are the same. So for the last 5 minutes, I think maybe a good thing to do. Oh, here you're actually cracking the 2-time pad. Anyway, I want to let you guys work on a problem in class together. So I'm going to stop the share, and could you just screenshot this? Screenshot this so that you guys can discuss these particular numbers, and then later, hopefully, this will help with your own homework. And for the last for 5 minutes, I'll put you in breakout rooms and see if you can solve this problem together. So you have 27 participants. Let's do 5 rooms. Okay, so I'll see you in 5 minutes. So were you guys able to solve it? People that have come back already? Anybody want to chat the answer? Okay, so I think most people are back now. So if you know the answer, do you want to say it or delete it? And how did you find it?
Hold on, let me see. I couldn't do it.
So it's okay if you couldn't figure it out, but I want to give anybody who did figure it out a chance to chat the answer. So going once, going twice.
Oh.
Okay.
Anyone figure it out?
Yeah, it
I
seems
have
like,
a number.
what was it?
I have it in hexadecimal, so I converted back to hexadecimal.
Mm-hmm.
So I got C4E9597 0EAD20D58. I can type it on the chat.
Oh, so C4E. Yeah, that's right. Congratulations. How did you do that?
So I converted the hexadecimal numbers to binary. Then I implemented the XOR calculation,
Mm-hmm.
and then I just converted back to hexadecimal.
Wow, did you do all that on paper?
Oh no, absolutely not. No.
Okay.
I mean,
So what
I mean,
software
no.
did you use? C++ or?
No, I just use like a online calculator actually.
Oh, okay. All right. Yeah, that's
Yeah,
fair.
but yeah.
So let me show you, like, you know, probably the most natural way to do this is in Python, but let me show you how you can do it in C or C++ also. So these numbers are pretty short. You know, I think an unsigned long is like 8 bytes. So as long as the hexadecimal is less than 8 bytes, you can do it like this. So you just you type in the hexadecimals, and then you take their XOR. And then I'm not sure how to do this with cout, but with printf, you know, here's the formatting string. This is for, you want a long in hexadecimal format, and then this is just a new line. So if I run this program,
Oh, okay.
Tell me the answer. You can screenshot that if you want to, everybody. 1, 2, 3, 4, 5. Okay, and now let's run it, and it gives the same answer that sorry, what's your name? Same answer that Lewis was telling us. Yeah.
Luis. Yeah, actually, so I had a question about the